This is lecture 3 of machine learning and Bayesian inference. In the last lecture, I really just reviewed the material that I introduced last year in the artificial intelligence course on supervised machine learning, and I introduced some other forms of learning, and I talked about some common notation that I'm going to be using for here on in. But the aim in this lecture is going to be to actually start putting all of this machine learning language into a probabilistic framework as originally promised, and to start seeing what we can then get as payback for doing that. One of the payoffs that we get for doing that is that, as I suggested earlier, we can start defining what it means to have optimal machine learning or optimal classification. And it's going to turn out that this business of doing learning by just choosing some specific parameter vector isn't necessarily the best way of going about things. But we're not quite there yet. That comes a little bit further down the line. Or the actual derivation for that comes a little bit further down the line. But I'm going to point out before I get there that that doesn't mean that learning by hunting for a parameter vector, hunting for a weight vector, is something that we shouldn't do. Okay, it's in practice still something that you can make an awful lot of progress with, mainly because doing the optimal thing in practice is often completely intractable. But anyway, that's getting ahead of where I really want to go today. So I want to start by just putting this into a probabilistic framework, and fairly quickly getting to the point, I hope, where we can see that that's actually quite a useful thing to do. The starting point here is incredibly straightforward. How do we put supervised machine learning into a probabilistic framework? Well, you always start with a set of labeled training data. And the way we get started on this is just to say, let's assume that that data is generated according to some unknown probability distribution, P of x and y. Okay, that is a distribution on the x's, the feature vectors that we're going to see, and y, their corresponding label. And those sets can be any of the kinds that we saw in the last lecture. Okay, let's just assume for now that we're going to do regression, because that's what I'm going to start by talking about. So the x's are real valued vectors and y is going to be a real number. And we then say, okay, there's an unknown probability distribution that governs how pairs of feature vector and label are generated. We have a collection of those. We have a training set. And we're going to assume that that training set was generated just by sampling this single fixed unknown distribution m times to get m training examples. And we're also going to make the assumption that these samples are independent and identically distributed. So they're independent of one another, they don't depend on each other, and each is distributed according to this single unknown probability distribution. This is a ubiquitous assumption, which is not always true. It is made because in order to do any kind of formal analysis of the learning algorithms that we're going to go about deriving, you need that assumption of independence. If you don't, then things become much harder to deal with. And similarly, if these things aren't identically distributed, which could be the case, for example, because the statistics are changing over time, things become much harder to deal with under that regime. So while there is work that relaxes the assumption of independence and work that relaxes the assumption of identical distribution, I'm not going to talk about that. That's something for another course. But once you've made that assumption, the key idea is that you now have this relationship. Okay, the probability of seeing your labeled training data is the product of the individual probabilities for each labeled training example, and that now just follows because they are IID, they are independent and identically distributed. Okay, so that is now our first step. We assume that data is generated at random by sampling some fixed probability distribution that's joint over the feature vectors and the label. As an example of this, I can just tell you how I generated the data for the initial one-dimensional example. Okay, I've already noted, I think, that I started with an unknown underlying function f that's actually a polynomial. That's what I used to generate this data. In fact, rather than call it f now, I'm actually going to call it h sub w, because it's something that I want to identify by guessing what the w is. Okay, so the translation there is that h sub w is actually the underlying polynomial relationship between the variables here, and it has parameters w, and in those 6 diagrams that I used earlier, that's actually giving me the equation for the dotted blue line. By choosing what those parameters are, by choosing the parameters of the actual underlying polynomial, I get to set the characteristics of the training data that I produce based on that bunch of parameters, okay, based on that polynomial. So by tweaking those parameters, I would get different training data sets in these 6 diagrams. I then just did something to make sure that the y values don't sit exactly on the dotted blue line. I needed to update or to modify the function values in some way. Now, the equation on here we're going to see a lot of, and we're also going to see a lot of its multi-dimensional bigger sibling. In fact, this is so ubiquitous that you should probably memorize the expression for the normal density. You're familiar with this from NST Maths and no doubt from a whole bunch of other courses because it's so fundamental. We have the normal density of mean, mu and variance, sigma squared. Mu sets the centre of the distribution and sigma squared sets its width. This is the expression for it, and it'd probably help you quite a lot if you memorize it. The idea then is simply to use it to modify the initial function values that I get by choosing some underlying bunch of parameters w. So I sample the x-axis according to a uniform density on the interval 0 to 3. Okay, that gives me a bunch of x values, a bunch of single features for this particular straightforward one-dimensional example. I plug each of those into my unknown underlying function, h sub w, and then I take a sample from the normal distribution, in this case with variance 0.1, and I add it to the value that my function tells me. Okay. So what I'm saying here is that for each example I sample this guy uniformly on the interval from 0 to 3. This is my unknown function, my dotted blue line, that is generated using a particular bunch of parameters w. This is my sample from the normal distribution, and I use that to modify the data so that this is the actual y label that I get. Okay? Now, what's actually happening to the normal density here? Well, all I'm doing is shifting it by this much. So if its mean was 0 before, now its mean is the value of h sub w. And because this is a linear transformation, all I'm doing is adding its variance in this case, because I'm not multiplying by anything, I'm just adding its variance stays the same. And that means that the density of y is normal with a mean that's equal to this and the same variance that we started out with. Okay, and that's summarized in the box at the bottom of this slide. Okay, all that's happened here is that what was previously mu has been replaced by the value of the function h sub w, and we're actually talking about the probability density of y, not x, so y has appeared here. Okay, that should be clear when you compare these two slides. Now, that's how y is then distributed depending on some fixed value of x that you started with. Okay, each time you sample something to get a training example, each time you sample something on the line 0 to 3, you get a value of x, and then you sample y. Okay, so that y has a density that's conditional on x, so we can write it like this. Now, with the w there, I'm being slightly naughty. It's something that I picked in advance. It's not, strictly speaking, a random variable. It will be in a minute. Okay, we're going to widen the discussion a little bit further down the line. So, strictly speaking, I shouldn't write it there. Sometimes you will find in the literature that in order to draw a distinction between things that are random variables and things that are just chosen parameters, people will actually put a semicolon in order to separate the two. Okay, I'm probably going to do that later on when we get more parameters and more random variables involved, but for now I'll let you tell what that is from context. Okay, but we will inevitably, because w actually appears in here, change this posterior density for the ith y by changing w, so it's a parameter. And because all we're doing is shifting the mean and leaving the variance the same, this is the expression that we now have for that posterior distribution for the ith value of y. Now that's called the likelihood, and it's often written in a slightly different way. Okay, it's often written like this to emphasize the fact that it depends on what w is, and that kind of makes sense because ultimately it's w that we're going to try and choose, and we'll see that in a moment. But I'm going to just continue writing it as probability density. There's also an important point here, which is to remember that the form that the likelihood take now immediately depends entirely on how you've chosen to model the data. You'll get different likelihood functions depending on what assumptions you make about how this data is generated. Okay? What we've done here is to introduce a model for how this data is generated in the first place. Now, what we're going to do is keep up with this assumption that the parameters in w are fixed but hidden from us, and now extend this idea of likelihood to the entire training set. And that's pretty straightforward because we've just established that because we're going to assume that the data is independent and identically distributed, we can just take the product of the joint probability value for all of the individual examples in the training set. Now, once again, everything depends on w, which is now a parameter. So we can now write that the probability of the training data that we see, given the value of this parameter w, is just the product of that joint probability taken across all m examples. Now, hopefully by now you've had a good look at the handout on basic probability manipulations. Once again, if you have things with conditionals in them, they're still probability distributions, and you can manipulate them as such. And in this case, what that means is that you're used to seeing that the probability of A and B is the probability of A given B times the probability of B. Okay, and everyone's happy with that. What I'm using now is the fact that if you've got the probability of A and B given C, it splits in essentially the same way. So you have the probability of A given B and C times the probability of B given C. And that's what's used in the second line in this series of three equations here. And in the final line, you make the assumption, which seems pretty reasonable, which is that the x values don't depend on your value for w, so they are independent, and the probability of the ith x vector given w is just the probability of the ith x vector. So it's probably worth just recapping exactly what we've got here. Okay, what I've suggested is this. We want to model the data as being probabilistically generated. What I've suggested is that you hypothesize a particular functional relationship between the x's and the y's, and that has these parameters w. And that means that the relationship between them is given by h sub w. Okay, step one. I've then said, model the generation of those x's as being something that happens by picking them according to some distribution. Okay, in this specific example that I'm using, the uniform density between 0 and 3, because we only have one x value, and we sample that m times in order to form the training set. The next step is, if we want m examples in the training set, we sample m times to get m x values. For each of those, we get the value corresponding for h sub w. And then for each of those, we sample the normal density of zero mean and some specified variance, and add that to the actual value of h sub w. And that gives us m pairs of x and y, which are generated by putting the x through h sub w and then adding some noise to the result. And if we make the standard underlying assumption that we're generating everything IID, independently and identically distributed, we can then write that the probability of the training set we got, given the w we started in order to generate this stuff, takes this form. Okay, and it includes the likelihood that we've just derived for the specific example, which comes from the density of the noise that we choose to use in this process. Now, in a nutshell, what that says is that you can pick a W and use it to generate a training set. Okay, it's an entirely mechanistic process. You've made a model of how data is generated, and the data that you get depends on the parameters that you start off with. If you use some different parameters in the specific running example, you get a different underlying polynomial, and you'll get a different training set generated according to your model of the data. Now you just need to flip around slightly the way that you think about this. Okay? On the one hand, I can pick the W and give you some data. What you're trying to do is guess what the W is, because I'm not telling you. You just get the data. So instead of thinking about this as some kind of process of generation, you can think to yourself, okay, if I've just got the data, can I work out which value of W is most likely to have generated it? I want you to stop and think about that for a moment. Okay? I've described to you a mechanistic process that lets me choose some parameters and generate some data that I can give to you. You can think about supervised learning as the question of, having got that data from me, can you work out which bunch of parameters was most likely to have generated it? Okay? This is supervised learning in a nutshell, if you like. You get some data, you want to choose something that fits it. Okay? So you propose what you think is a good method for having generated that data and choose the parameters that are the most likely to have given it to you. Now we can sum that up in this equation here. We choose our optimal guess, wopt, for what these parameters are. I don't know if you've seen the argmax notation before. Argmax with something underneath it means find the value of that thing, in this case w, that maximizes the expression. Okay, argmax is the value of w in this case that maximizes the expression. And I'm suggesting that you choose the w as your guess, which is the one that maximizes the probability of the data had it been generated using that w. And this is called a maximum likelihood training algorithm. Surprise, surprise. The question that then arises is, how would you actually do that? Now, that may seem a little bit opaque at the minute, but bear with me for another couple of slides and we'll see that we get actually quite a surprising and nice answer. Let's look at this line by line. The first line here is just writing my definition of the maximum likelihood training algorithm. The second line, I've replaced the probability of the data given w with the expression that we derived a couple of slides back. Now, I'm using a standard trick here, which is that if you're trying to maximize something, you can maximize its log. Okay, and that's nice because logs turn products into sums. And they also get rid of exponentials for you because log exp just cancels out. So to get from the second line to the third line here, I've just said, well, instead of argmaxing over w, we can argmax over w with the log of the expression we're interested in. And that turns the product into a sum. And it also splits the product of p of y given x and w and p of x into a sum. So we end up with these two summations. And then because the second summation here doesn't depend on w, the thing that we're trying to maximize over, we can just get rid of it. Okay? So that gets us to here. We're only maximizing over the sum of the log of the likelihood function that we derived a little bit earlier. Okay, so two standard tricks there. Firstly, if you want to maximize something, you can maximize its logarithm. That's nice because it turns products into sums. And secondly, you can drop parts of the expression that don't depend on the thing that you're maximizing over. At this point, you go back a couple of slides and you pick up the expression that was derived for the likelihood. And you plug that in. And you get the first line here. Now, what's going on here? Okay, well, what essentially we've done, let's just go back. Here we've got the log of that likelihood. And if we go back and look at what the likelihood actually is, it's this. Okay? So when you take the log of this big expression here, you get the log of this term plus the log of exp of something, and the log and the exp cancel out. So the second term is just the stuff that's in the brackets here. Okay, and you get the sum of those. So if we wind forward, that's exactly what we've got here. Now once again, the first term doesn't depend on W, so we can ignore that. And then the second term, well, it's got a negative. So instead of having an argmax, we can drop the negative and turn it into an argmin. And we get our final answer. Now, what does this say? It shows something really quite nice. It says that the maximum likelihood training algorithm in this case is obtained if you minimize the sum of the squared differences, which is exactly what we've been doing all along. Now, notice that that doesn't only apply for the simple one-dimensional example that I started with. Okay? It will apply to that, but it actually applies no matter what H sub W is, and no matter what the dimensionalities of our vectors, because all the expressions that I've used to derive this are general. They're not just things that apply in that basic one-dimensional case. So this is a general training algorithm, okay, for any dimensionality of the x vectors and any collection of parameterized functions, functions parameterized by the parameters w that we care to think of. And I think that's really quite a nice result. Okay, we first chose the sum of squared errors because it seemed like a sensible thing to do. It was going to be a bigger error the further away our predictions using H sub w got from the actual values in the training set. And that seemed quite nice. But now we've kind of flipped things over a bit and gone into a domain where essentially by choosing the kinds of functions H sub w that we can use and the kinds of noise that we think are being used to modify its outputs, we end up with a model for how the training data is being generated, and then by trying to choose the parameters that would be the most likely ones that have generated that data, we come up with an algorithm that says, look, you should minimize the sum of squared errors. Okay, we didn't just pluck this out of thin air anymore. We started with the model of the data and did something sensible with it. Now, this is important because it uncovers a hidden assumption. You can, of course, just use the sum of squared errors because it seems like a sensible thing to do. But now what it's telling you is that thinking about data this way, it means you're assuming that the noise is Gaussian. Okay? It means that your assumption is that it's a normal density that's being used to modify the y values by making them noisy. That may or may not be a good assumption to make. You may immediately want to appeal to the central limit theorem. This is dangerous. In practice, noise in training data, and people have studied this, is not necessarily Gaussian. Okay, it's not necessarily normally distributed. There could be any other number of densities that govern that noise depending on the process that's being used to generate the data. And assuming that it's Gaussian may be appropriate, but it might not be. If you know that the noise is non-Gaussian, it is now open to you to modify this derivation, and what you will get is a different form for the error that you're supposed to be minimizing. And that's important. Okay, sometimes it is not appropriate to assume that noise is Gaussian, and you are essentially making that assumption by minimizing the sum of the squared errors. There's also a second assumption here, which is that maximizing likelihood is the right thing to do. Okay, what we've done here is to find the likelihood and maximize that, again because it seems sensible, but we should probably question whether or not there's something better that we could do in that respect as well. So let's now take a look at that. My assumption about how the data is generated started with me picking a specific value for the parameters w before generating the data that I would show you. I noted that that means that w is essentially a parameter because it's not a random variable. It doesn't have a probability distribution. Because I'm not telling you what it is or how I'm picking it, it is something that is uncertain to you. So the way in which I choose to pick those parameters w before generating some data with it to show you should itself have a probability distribution. Okay. So the next step here is to say, let's put a probability distribution on this parameter vector w. Now once again, we're going to make that a Gaussian. Now, because it's a vector, we need the multidimensional Gaussian, which may be something that you're less familiar with. Okay, but the point now is that we're just going to say, every time I generate some data to show you, in order to model the fact that you are uncertain about what parameter vector I might pick, what I'm actually going to be doing is picking it according to some probability distribution and then using whatever I get to generate the data. Okay, and that allows you to model uncertainty in the way in which I'm picking that parameter vector. So we're going to say that the parameter vector is now being selected according to a normal distribution as well. And the normal distribution in many dimensions looks very much like the normal distribution in one dimension, except the mean now becomes a vector mu, and instead of just a covariance sigma squared, we now have a covariance matrix, which is capital Sigma in bold. And hopefully this doesn't look too scary. Essentially all that's happened is that whereas previously we had 1 over sigma squared in the one-dimensional version, now it's the covariance matrix, but instead of 1 over it, it's inverse, unsurprisingly. Previously we had x minus mu squared, and now that's come into this matrix-oriented version that has, in this case, w minus mu, because it's the variable of interest is w not x, and squaring it involves putting one copy on each side of the covariance matrix. And previously we had, let's go back and verify. Previously we just had a variance here inside the square root. Well, okay, we can't just put a covariance matrix inside a square root because a square root is expecting just to take the square root of a number. So now this is the determinant. Okay, and we have a d, which is the dimension of the parameter vector w here. Okay. Again, if you've forgotten how to deal with multidimensional normal distributions, take a look at your notes for NST Maths or the textbook of your choice. It shouldn't be surprising that when you plot one of these things, it just looks like a normal distribution extended into 2 or more dimensions. Okay, so I plotted a couple of possibilities here. If you change mu, you change where the center of that distribution is, and if you change the covariance matrix, you change not just the width of the distribution in any simple way, but the relative widths on different axes and the general orientation of this Gaussian within multiple dimensions. Okay? As luck would have it, most of the time when we need to use this, the covariance matrix will be diagonal, which makes your life a lot easier, and quite often it will just be the identity matrix, or possibly a scaled identity matrix, meaning that everything's nice and symmetrical like in the plot on the left, and that makes it a bit easier to deal with. Okay, the key idea now is that we make w a random variable, and we say that it's chosen according to this kind of normal density in the relevant number of dimensions. Now that allows us to do something slightly different. What I'm going to do is say, well, actually, my what's now called a prior probability for W is going to be the multidimensional normal density with a zero mean vector and a covariance matrix that's just some constant times the identity matrix. Okay, so if you plug those into the general expression on the previous slide, you get this probability here for how W is being chosen. So essentially, what that means is there's an assumption being built in here that before you get to see any data, the way in which these parameters are being chosen is probably going to be in such a way that most of them are quite small, because this is zero mean. So you're not going to expect to see values for these weights W that are a long way from zero, okay, because at that point the curve is going to have become small, there's not much probability there. And also that it's going to be a vector that's been chosen sort of quite close to the zero vector, but you're not preferring any particular direction, okay, because it's a symmetric covariance matrix. And lambda here is just going to be setting essentially how far out you think, or how far away from zero you think these weights might be likely to fall when the weight vector is chosen from this density. Now this allows us to do something, or a couple of things that are really quite nice. We can slightly flip again the way in which we think about this, and I hope that earlier when I was talking about the maximum likelihood approach that this would have crossed your mind. For maximum likelihood, we were maximizing the probability of S given W. Okay, the probability that had I chosen a particular W to start with, you would have got to have seen some particular bunch of data. But I hope it crossed your mind that perhaps a better thing to do would be to maximize the probability of W given S. Okay, if I show you the data, which W is most likely given the data that you've seen. Okay, we're flipping things around using Bayes' theorem. Okay, instead of probability of S given W, we want the probability of W given S. Okay, that gives us a maximum a posteriori algorithm. Okay, again, it's a slight change of perspective, but it seems like a sensible thing to do. Okay, it seems sensible to me to say, what's the probability of the W given that you've seen some data that was generated by a value of W, rather than what's the probability of the data conditional on W. Now, again, we can carry this through in quite a straightforward way. This is what we want. This is the maximum a posteriori algorithm, argmax of P of W given S. We can just apply Bayes' theorem to that, which gives us this. And because we're maximizing, we can just take the log, which gives us this. Now here, in taking the log, I end up with an extra term, which is just log P of S, but that doesn't depend on W, so we could get rid of it. Okay, all the same tricks as before. And then everything essentially goes through the same way. This is now exactly the quantity that we saw previously. Okay, all we've got now is argmax of exactly what we saw the last time, and then this extra term here. And if you carry the derivation through, you end up with the final equation on this slide. And here, what this is saying is that you should minimize exactly the same thing that we saw before, the sum of the squared differences. Okay. In this case, we're still working with the assumption that noise is normal distributed. Okay, I haven't changed that assumption here. But from the prior, from the fact that we've now introduced a distribution on the weight vectors, we get this extra term here. Now, some of you may have seen this before if you've done other courses that have involved supervised machine learning, you may recognize this as something called weight decay. Now, once again, this idea was introduced decades ago without reference to this particular derivation by quite a lot of people. People introduced this extra term into the error measure that's being minimized in order to do regularization. What do I mean by that? Well, earlier I talked about overfitting, about the function that you choose getting sufficiently complex that it was trying to learn the noise and not just the underlying relationship. People realized that a lot of the time, if you tried to constrain weight values to be small, you only got smooth functions in trying to fit the data. And because that encouraged smooth functions, you would tend not to fit the noise so much and to actually get better performance. So they introduced this extra term to try and keep the weights small. And they introduced this parameter lambda as a means of controlling how much you enforced small weights in order to actually end up getting smooth functions. Okay, now that was called weight decay. And what we've now established is that this corresponds to another assumption, which is that the choice of W is being made according to a Gaussian distribution. So just to summarize what I'm talking about there, okay, that has appeared in the literature under the name of weight decay. And I should probably actually emphasize that regularizing in this way is in itself quite a big subject. Okay? The introduction of extra terms into a measure of error that you're trying to minimize is quite a deep subject in itself. And you get different regularization terms depending on what it is that you're actually trying to achieve. But this is probably the simplest possible way of doing it, okay, the weight decay approach. It was often proposed as a way of controlling the complexity of the function that you learn. And the extra parameter is something that was introduced simply to control that. But note also that we now have an interpretation for that extra parameter lambda. It's related to the width of the covariance that you're using for the prior for W. I will be speaking later in the course about how you actually might go about choosing a good value for the parameter lambda, because that in itself is quite an important point. And once again, this does hide some underlying assumptions. We're assuming that we expect some kinds of W to be governing the generation of the training data in preference to others. In this case, we're kind of making the assumption that the weight values are likely to be quite small. And we're also assuming that they themselves have the Gaussian distribution, and those assumptions may or may not be appropriate. Now, all of that has been based on the idea of doing a regression. Okay. Here, the use of a normal density to model noise in the data seems perfectly sensible. The likelihood, the probability of y given x and w is a density, okay, and y can then take any value on the real line. And that density can be anything we want to choose. It just has to be non-negative and integrate to 1. But the question now arises of what we can do in order to extend these ideas into the realm of classification. Because if we want our labels not to be arbitrary real numbers, but just to be classes, class 1 versus class 2 for the two-class classification problem, or one of a number of classes for the multi-class classification problem, just dealing with Gaussian noise is no longer something that seems so sensible. Just taking a label that says it's class 1 or class 2 and adding some normal distributed noise to it doesn't make any sense anymore. So we need to think about a different way of modelling the generation of data that's in categories, okay, that's in classes. So let's now see how we can fix this, and in order to do that, let's assume that we have a two-class classification problem. Now, we're not doing regression. What we want as an output, or as a label now, in our training set is a 1 or a 0, denoting it's class 1 or it's class 2. That means that the likelihood has to take a different form, okay? The likelihood, the probability of the y given the x and the w now can't give y just any real value. Y now has to be 1 or 0, okay, because it's indicating class 1 or class 2. Okay, so this guy now has to be somewhat different, and it has to have this property because we're only talking about class 1 or class 0. There is no other option. So the probability of being in class 1 has to be 1 minus the probability of being in class 0. How do we keep this idea of generating data in a random way, but actually modify the likelihood to have this property? Well, a straightforward way of doing it is to use something like this. Okay, so we still have this unknown underlying function, this unknown underlying model for the data, which can be real valued. Okay, the function h sub w here can still be real valued. That's completely fine because we're squashing it using this thing called the sigmoid function here. Now, the sigmoid function has a value that's real and between 0 and 1, and its argument, the value of h sub w of x, can be any real number at all. Okay, so that allows us to keep the idea that this underlying function h sub w is being used as some kind of fundamental data generation process, but the sigmoid function then turns this likelihood into something that we can use, okay, namely the probability that you're in class 1 given x and w. Now, the sigmoid function looks like this in the top panel, where it's been plotted for a bunch of different values of theta, its parameter. Theta will generally leave out, okay? It's here for now, just to illustrate that you can get this control over the sigmoid function. But as you can see, what it does is that for an argument that's positive, it gives you a probability of close to 1, and for an argument that's negative, it gives you a probability that's close to 0. Okay? Or in other words, we can still use this to model the generation of data. I can still have some parameters w that I choose but don't tell you about. I can still use that to get values of h sub w for my x's in my training set, and then I put them through the sigmoid function. I get a probability for each of those guys to be labelled as class 1. That could be close to 1 or close to 0 or close to a half. But now here's the key point. In order to generate the label in this model of generating data, I give it class 1 with the probability specified by the likelihood and class 0 otherwise. So it's like looking at the value of the likelihood and flipping a biased coin with that value. And if the coin comes up heads, I label class 1, otherwise I label class 0. Okay. So once again, we've got a model for how there might be noise, how there might be perturbation in the way in which the labeling of the data is produced. Rather than just perturbing it by a real number, we get a value for what is the probability that this is in class 1, and we flip a biased coin with that probability in order to get the label. So what I've done in the lower panel here is just illustrated that for the classification version of the simple running example with one dimension. Here again on the x-axis I have individual values of x which are now just one-dimensional. Those are used to generate my training examples, which are the blue circles and the red crosses. The dotted blue line again is my underlying function h sub w that I've generated choosing some particular parameters w. Now each time I generate something on the x-axis, let's take this guy for example. He's a training example, so he has a value of x that's down here. At that point, my underlying function h sub w is a little bit greater than 0, but not much. So once I stick it through the sigmoid function, it's a little bit to the positive side of 0. So I have a fairly, well, I have a better than half probability of labeling it in class 1, so I flip a coin. Now in this case, it's actually been labelled in class 2. My coin flip came up the wrong way. And that's not surprising. It's not surprising that we see some apparently anomalous examples here. Generally in areas where the dotted line is actually quite close to 0. Okay, so we're in this kind of part of the sigmoid function. Okay, the coin flip can go either way. If I look up here, for example, my underlying relationship is getting quite positive now. It's very likely that data up here, when I flip the coin, will actually be put into class 1. But wherever we have the situation like here, where my underlying function is around 0, we're essentially doing a fair coin flip in order to get the label. So we will occasionally see anomalies. But then down here, for example, when the underlying function is going very negative, we're down in this kind of area of the sigmoid, and everything is very likely to be labelled as class 2. Okay, so once again, it's a model for generating data, and the sigmoid is now being used to squash the underlying function h sub w into a probability between 0 and 1, and that allows us to model the fact that we will sometimes get a mislabeling. Now, I will leave you for this lecture with this diagram, which does the same thing, but in 2 dimensions and with a linear relationship for h sub w. Okay, so now I have 2 input features, x1 and x2, that are in the plane. My h sub w is a linear function of those inputs that itself has now 3 parameters, a bias w0 and the 2 weights w1, w2. And the generation of the data here is being achieved by randomly selecting x1 and x2 according to some distribution on the plane, putting each example through a linear relationship, okay, which is identified on the plane here by this straight line, putting the value that results through the sigmoid, and then doing this process of doing the biased coin flip. And as you can see, rather than ending up with data that's specifically one class on one side of the dividing line and the other class on the other side of the dividing line, we have some examples that are classified in a sense the wrong way because we are modelling noise in that classification using the sigmoid function. Now I'd like you to think about this diagram before we get into the next lecture, and make sure you understand what is actually going on here. Okay, I have set up a model for how the data is generated. My model says that my classes are linearly separable, but there is noise in the training data that I'm going to get that is modelled in this particular way. And that means that my model of the training data that I get to see looks like this, with possibly misclassified examples that are apparently not on the right side of the line. Okay, think about this, make sure you understand how this data generation model works.